Okay, we've got some space to work with now, so let's look at the constrained problem. And so what we want to do, I'm not going to write the whole thing down again here. So it's the same statement, except that we have to change a couple of things. We have to change this to maximization of an objective function subject to a constraint. And then I have to say something about that constraint function being differentiable. And then, of course, I have to adjust the conclusion. So let's say that we're going to change P to a constrained problem. And that's going to be to maximize our objective function subject to a constraint. Say equals B. We'll often see that as just 0, kind of normalization to 0, because here we could pull the B over to this side, make it part of the G function, and have 0 over here. But I think it might actually be useful to leave the B over here. Where G So G, just like the objective function, has both decision variables and parameters in it in general. So sometimes we see constraint functions that don't have that, but typically, often we do. So here we have this, and we're going to say this is also a C1 function, continuously differentiable, just like over here with the objective function. Everything else is the same. This says it's C1. The solution function's still got to be differentiable. And so now we look at the conclusion. So let's put the conclusion in here. And the conclusion is again going to be something about the derivative of the objective function with respect to a parameter value. And that's going to be, as it turns out, the derivative of the objective function with respect to the parameter. No surprise there. But now, instead of getting just that derivative, we also have something involving the constraint. Let me give myself a little more space there. Let's put that minus sign here and put the rest of this over here. So this is lambda times the partial of the constraint function with respect to GI. So not quite as simple as over here. I mean, it looks still fairly simple, but it's not nearly as obvious that this should be the derivative of the value function as perhaps this might be. So let's see if we can give a proof of this. And of course, we're going to start the same way. We have the derivative of the value function with respect to the parameter theta I is, of course, going to be derivative of f with respect to theta I plus, again, let me leave myself a little more space here, plus the sum here. So it's going to be plus the sum, j equals 1 to n, partial of f with respect to x, j, partial of x hat with respect to theta I. And that's, of course, because the value function is still, still the value function. It's just that we've added this constraint onto here. And so let's see what this is. This is still going to be partial of f with respect to theta I. Now, what about this? Well, what we did was we used the first order condition to transform this here into zeros, okay, in the sum, to transform this into zeros so that this whole term was zero. We can't do that here because the partials of the derivatives of the objective function with respect to the decision variables, those derivatives aren't going to be zero in the first order conditions. What are the first order conditions here? Well, the first order conditions, let's actually put those down here. So let's draw a line here, and I'm doing this because I'll probably use most of the space over here, but we've got a little space to work with here. So let's just note that the first order conditions for this constrained problem, just remind ourselves that the first order condition is that the gradient of f should be equal to lambda times the gradient of g for some Lagrange multiplier, some scalar lambda, scalar multiple. And of course, that's to say that partial of f with respect to xj is equal to lambda partial of g with respect to xj, j equals 1 out to n. So I can replace this with lambda times this derivative here for every j. And so let's do that. Let's say this is now the sum, j equals 1 to n, lambda partial of g with respect to xj, and then partial xj with respect to theta I. So that really didn't get us quite as far as we got as quickly as we did over here, because we've still got something that doesn't look quite like this, and we couldn't make it zero and drop it out. So what can we do? Well, the first thing we can do is we can take the lambda and put it out in front here. Okay, so let's just do that. Don't have to do that, but I think it might simplify things a little bit. So let's put the lambda out here. Now we have this sum here. So let's see if we can figure out what this sum is. So what I'm going to do is, first I'm going to just here write again partial f with respect to theta I. That part's not going to change. And then I have plus, and I'm going to have a lambda, but I have to take this sum and figure out if I can turn this sum into minus the derivative of g with respect to theta I, because the lambda and the lambda here, I got a minus sign. So this sum is going to have to turn out to be the same as this derivative here. So you'll notice that this gives us the derivatives of the g function with respect to all the x variables and with respect to the theta variables. All theta variable, the one variable that we're taking the derivative with respect to. The other thetas are, of course, being held fixed here. And so that's all the variables in our objective function. And so let's write the sum j equals 1 to n. And let's write the Taylor polynomial for the g function. So the Taylor polynomial here, we're going to end up with it's really the differential here we're getting. So we're going to have the, here delta xj, and then we're going to have plus the derivative g with respect to theta I, delta theta I. And so when the parameter changes and the x's adjust, when the decision maker adjusts the x's, the decision variables, so that the first order conditions are still satisfied. In other words, the decision maker responds to the parameter change by changing his or her decisions to again be optimum, then it's going to be the case that these always satisfy the constraint. All right? The theta and the x's are always going to satisfy our constraint. So this provides the change in G, and in fact, of course, we could even write this as that's the change in G that takes place when we have these finite changes here. And now let's add in the remainder term, and I'll leave out the variables here, and that's got to be 0. It's got to be the case that as we adjust the theta and the xj's, that in the limit, that's got to be, in fact, this has got to be the case for finite changes if we have the remainder term in here. So now let's just divide everything by theta I. Here, here, I said theta I, but it's actually delta theta I. So I'm going to divide everything by delta theta I. So when I divide this by delta theta I, this has delta theta I divided by delta theta I, which is 1, so that's just going to drop out. When I take the remainder term and divide by delta theta I, that is going to go to 0 as the delta theta I goes to 0. The limit will be 0, and so I'm going to have that drop out. And so what I'm going to be left with is a 1 here, so this is just the partial of G with respect to theta I, and then here I'm going to have delta xj over delta theta I. So let's put that back in over here. Let's just put the delta theta I back in there. And of course, when then we take the limit as delta theta I goes to 0, this is going to be the derivative. So this will be the derivative of xj with respect to theta I. So now I have the sum of the partial of G with respect to x times the partial of x with respect to theta plus partial of G with respect to theta equals 0. Or, if you like, this is minus this. I'm not doing a very good job of that. Okay, minus. All right? So this sum here is equal to the negative of this partial here, and that's exactly what we wanted, right? We have here the sum of the partials of G with respect to the x's and the x's with respect to the thetas, and we've said that's equal to minus the partial of G with respect to theta I, which is this. So what we have is the sum, j equals 1 to n. In fact, let's just write this as minus G with respect to theta I. And that's it. That gives us the conclusion, and that completes the proof. So it turns out that the method of proof, the approach, is really the same as over here. We take the derivative of the value function with respect to the theta, the parameter, which is changing, and we have to take that then through here. So we're using the chain rule here. And by doing that, we then apply the first order condition to the derivatives that we get. And here, a little more complicated, but here we end up with lambda times the negative of this derivative here. So that gives us the conclusion of the envelope theorem for a constrained problem, and that's one constraint. So let's kind of finish up with the fully general form of the envelope theorem by looking at the situation with multiple constraints. So what do I need to do to change this to multiple constraints? We've got the index I on the parameters and the index j on the decision variable. So let's use the index k, let's say, for parameters, for constraints. And I'll put that as a superscript on the functions g. So now I have subject to gk equals bk, k equals 1 to L, let's say, because I've already used N and M. So I have L constraints, and this is the form of each constraint. This all looks the same. G is now a function that maps into, well, let's just put the K up here, and then it's still mapping into R, and we still have K going from 1 to L. And so then the conclusion is again going to be that the derivative of the value function with respect to a parameter is just the derivative of the objective function with respect to that parameter minus some expression with the constraint derivatives, but it's not going to be this expression because this is only one constraint. In fact, let's replace this with the sum. K equals 1 to L lambda K times the derivative of g with respect to theta. So we're still working with the derivatives of g with respect to theta as we were before, as we did here, but now there's a bunch of g functions, and so we have a Lagrange multiplier for each of the constraints, and so our envelope theorem tells us that the derivative of the value function will be this expression with a linear combination of the constraint derivatives, the derivatives of the constraint function. And so let's see how we get that in terms of altering the proof. And that's pretty straightforward as well. The only really tricky thing in any of these proofs was this step here. This step here is pretty straightforward, but let's carry it out. So here we have this first line is still the same, just as it was all the way through. First line is the same, just the same as it was over here, same as it is here. We take the derivative of the objective function with respect to each of its variables, the parameter and the x's, and then we need to apply the chain rule here. And but then at this step here, we now need to apply our first order condition. And so let's put the new first order condition for the multi-constraint problem down here. And that is that the gradient of f is equal to the sum k equals 1 to L lambda k gradient gk. And writing that in terms of partial derivatives, it says that the derivative of f with respect to xj is equal to the sum k equals 1 to L of lambda k partial of gk with respect to xj. So the partial of f with respect to xj, I now need to put in not just lambda times the gradient of g, but the sum of the Lagrange lambdas times the appropriate g's. So we need to change this. So let's take this out. In fact, let's just take this whole sum out here. Okay, we've cleaned things up a little bit here. And so, again, we need to replace the derivative of the objective function with respect to the x variable with this linear combination over here. So that's going to be the sum j equals 1 to n. And now we're going to have the sum k equals 1 to L lambda k partial of gk with respect to xj, partial xj hat, let's say, with respect to theta I. And now I'm going to, in effect, do what I did before when I took the lambda out in front, I'm going to reverse the order of the summations, and we'll write this as sum k equals 1 to L lambda k sum j equals 1 to n partial gk partial xj hat with respect to theta I. And now, of course, this part here is the same as the part that we transformed in the previous version of the proof with only the one constraint. And we transformed that into the negative of the derivative of g with respect to theta I. And so we now need to do that for each constraint, k equals 1 to L. So that means this is now going to be partial of f with respect to theta I plus the sum k equals 1 to L lambda k minus partial of gk with respect to theta I. So I just did the same thing we did in the proof a moment ago with the one constraint. I just did that with every one of the L constraints. And so again, now you can see that this is the same as what we have up here because we have the partial of f with respect to theta. We have sum of the lambdas times the partials of g's. Here I've got the minus in here. Here the minus is here. So we've got what we said we were going to get, and we've completed the proof. Well, before we move on to looking at some applications, I wanted to do something that I said I was going to do, and that is I want to put the formal statement of the envelope theorem here on the screen. And so that's what we have here. And so this has all the details, most of which I had already expressed in what we did over here, where we don't have the constraints added yet. And then when we added the constraints, which I've taken off to replace with the statement of the theorem here, and you'll notice it's really exactly the same. I've added a couple of qualifications, but in particular, the one thing that I want to point out that I've put here and that I didn't stress before is that the envelope theorem is very much a local result, local statement. So it tells us what happens in a neighborhood of or near particular parameter values that I've used theta bar to represent, and particular values of the determined variables, or what I call the decision variables here, the x bar. So it tells us what's happening locally around those, and that may not persist, and in fact it's not going to persist exactly as we move to different parameter values and resulting different x's. So here we have an exact and formal statement of the theorem, and now I think we're prepared to move on to several applications of the envelope theorem in economics. So we'll take everything off here, we'll come back and we'll do that.